Okay, so I've got a couple things I want to accomplish today. First thing is you'll notice that on the test yesterday there was not a portion where your name and the bonus was. Okay? That's because I cut the 2 pages up into one day and then another. So today we've got that page to do, which is one problem and the bonuses. Okay? There are 3 bonuses though. Jeepers. Okay? So what we're going to do is I am going to deliver some notes on 3.1, so get ready for that. Okay? So I'm going to give you notes that probably might take about 10 minutes maybe. Is this?
This is the hour class.
This is the hour class. Great. We got plenty of time. Okay? So so the first thing I'm going to do is I'm going to talk about the next section a little bit. Okay? So get ready. Be section 3.1. I got some notes that you should have. So let's get ready to go. Quadratics. Okay. You may not believe it, but mathematics is created, and our goal here is to show you mathematics and get you good at mathematics that is useful in various ways. And not everything follows a line like we did last chapter. Okay? So we're going to get into a different type of graph, which you saw last night on your assignment. Okay? Quadratics, you've done a little bit of this before. I'm not going to assume that you remember something from 2 years ago. That's got me in trouble in the past, so we're going to go ahead and just kind of do a little bit of start from scratch, and then we'll get serious on Monday. So a quadratic is something of the equation looks like y equals ax squared plus bx plus c. Raise your hand if that looks familiar. Okay? Good. Good. It's in there somewhere. If you've gotten through Algebra 1, you've seen this before. Okay? The graph of any quadratic is the shape of any idea? But what's the word called? It starts with a P. Parabola. Parabolas, I think, are cool. I think it's much more interesting than a line. It's much more applicable than a line. The stuff that is actually related by a quadratic, there's tons and tons and tons of things. But the shape itself is kind of cool. Okay? So the one thing I want to start off with is an anatomy lesson. Like you guys have hands, feet, other arms, legs, other parts. Parabolas have parts as well. So we're just going to draw one. That wasn't overly smooth there, but I'll try and fix it. There we go. Okay. Parabolas, the thing that I like about parabolas is I can enlighten you guys to some parabolas that are all around you, that you've probably already used today. So far today in parabolas, I've already used at least 2 applications of parabolas. Okay? So, parabolas have up to 4 very important points. And all these points are at times more useful than others. These points right here. Anybody know what those are called? No, not these points. Don't cheat and look at your book. I appreciate you. Those are my x-intercepts. I appreciate you trying to get some. That's good. So these are x-intercepts. Just like lines have x-intercepts or an x-intercept, a parabola can have as many as 2. It can have 1 or it can have 0. We'll talk about that later. Okay? But the coordinates of these are special. Both of these have 0 for their y. How come that y is 0 on those points? You what? It doesn't cross the y? Well, just this point right here. My y value is my height. I know it's an x-intercept. I'm just trying to use different verbiage. Okay? If I'm on this, what's my height? 0. So my height is 0. That's why they're special. That's why they're special. This point right here, what is it? That's my y-intercept. And what's special about its coordinates? My x is 0. Because I didn't go left, I didn't go right. I just went up and down somewhere. Okay? And this point right here is often the most important point. What is that? It's sometimes a minimum, sometimes a maximum, but it's always called a vertex. Because sometimes my vertex represents a minimum point. Sometimes my vertex represents a maximum point. Okay? I'll teach you how to do that on Monday. But probably the most important part of a parabola is that line right there. Axis of symmetry. What does it mean if that's the axis of symmetry? Same on both sides. Same on both sides. So, if I have a point, like say, a point over here, there's a point on the other side the same distance away. If I have a point right here, there's a point on the other side the same distance away. So every parabola is symmetric. That's not optional. That's just how it is. It has to be that way. Okay? Is the human body symmetric?
Yes. No.
In ways, yes. In ways, no. How is it not? If my heart is more on the left side, okay? And then isn't your liver more on the right or something like that? Okay. But, insides are not very symmetric. And unless you had like a farm injury or something like that, and you don't have a hand or something or a foot, then most of us are symmetric. Okay? At least through the vertical plane. Okay? So that is kind of a get started thing.
What did you say the green was?
The green is just a demonstration of if a point is, like, say, if this point is a certain distance away on the left, then there's another point that same distance away on the right. That has to be the same on both sides. Like we don't sit here and our arm isn't, they're both the same. Okay, our eyes are both the same. Okay, our ears are both the same. Okay. While I'm thinking about it, this worksheet right here, you don't have to get it out, but a couple things I want to talk about. First of all of these should be parabolas. Okay? If they're not parabolas, I got bad news for you. You didn't plug in something right. And here's the thing that gives most people grief. Or if something's going to give you grief, it's going to be the negatives. If I grab my calculator and I type in -4 squared, what's it going to give me? It's actually going to give me -16. If you try it with your calculator, it'll give you -16. Yep. Yeah, this one, it'll give you -16. So the problem here is if you try and do too much with a calculator and don't use your head, you're going to make silly mistakes. Because this one, we know that if we square a number, take it times itself, what kind of number do we always get? positive. Okay? If you want to do it with your calculator, you've got to put parentheses around it. So it squares the negative also. But I would hope that everybody in here can do that in your head on every single one of these problems. If I take -4, if I square -4, what do I get? 16. 4 times 4, 16. Don't have to worry about the negative because it's going to be gone anyway. So 16, so you've got to square it first and then take half of that. Half of 16, 8. So my advice here, folks, try and do more with your head. The stuff I've seen people do in the last few days on their calculator is kind of scary. I saw -3 times 2. Not necessarily anybody in here, I'm not saying that, but just because people get in the habit. So just do these in your head, if at all possible. Because what my goal is with this is when we're all done with this, which you're going to finish this for today, this is your assignment for the weekend, you will not do the back. So are you doing the back? No. So that I don't get 10 questions about that. I'm hoping that if you come in with this on Monday, you'll see parabolas of all different shapes and sizes. And that's going to lead our lecture on Monday. Okay? Okay. Let's get back to some things here. So, parabolas. This is where I think it gets cool. Applications. Why are they important? First, projectile motion. Projectile motion is probably one of the most common. If I go up to the top of a school or top of a building and I throw something up, it's going to go ahead and follow the shape of a parabola. That's just how it is. Okay? Even if you throw it outwards, it's going to follow the shape of a parabola. Okay? Molly might be sitting there thinking, now wait a minute, my golf ball doesn't travel the shape of a parabola. Because it doesn't. And there's a reason for that. Don't draw this or anything. Let's just talk about it. So if I hit a golf ball, it doesn't go like this. Okay? Yeah, for some of you guys it might go strong left or strong right, but that's not what we're talking about. What usually happens is it goes and then drops. Would you agree with that? I just got done saying that projectiles follow the shape of a parabola, and am I lying to you? Well, what's considered here, or what makes it go like this? Air. You got all these dimples on the surface of a golf ball that's trying to get as much distance as possible, and to get that, they want lift, and they want, it's gonna lift, it's gonna keep going, and then finally it starts losing speed and it just drops. So, projectile motion, that is ignoring air resistance. But if I go up and I take Owen to the top of the school and I throw him off the top, air resistance probably isn't going to come into a big play by the time he hits the ground. Okay, now don't do that, of course. Okay, reminds me of a story about a gerbil, but I'm recording right now, so we'll tell you that story some other time. So anyway, any projectile motion is going to follow that in some way, shape, or form. Okay? Other things, which I think are just, bridges. I'll save the cool part for last. Bridges are a great example of some uses of parabolas. Okay? Because if you take a look at it, yeah, there's a parabola. A parabola is very good at displacing force from one location to the outside. Okay? In this case, this is a parabolic arch girder, and then you've got all these support cables to support that straight deck. Parabola is very good at taking all this force and applying it to the outside. Okay? And while this is not exactly a parabola, it is something that is very, very, very close. You have hanging cables, and this is a suspension bridge. I think bridges are cool. I just think they're kind of neat. The mathematics and actually they're designed to be beautiful as well. Okay. I'm going to go ahead and I'm going to put it this way. Vomit, comet. Okay. Now, vomit comet is kind of a crude term that's used in the field for when you're giving somebody training as far as weightlessness goes. Okay? For astronauts to get used to weightlessness, they did a couple different things. They would do things underwater, and they'd give them the right buoyancy, so they were kind of floating around, bouncing around. But what they would also do is they would put them in an airplane that was traveling the path of a parabola. If you look at this part right here, that's a parabola. If you follow the right path, you will have weightlessness on the way down. And to kind of explain it, if I had like a tennis ball in a box, if I dropped the box at the right height, would the ball be floating in the box? Yeah, that's what they're doing here. Okay? So if you see some weightlessness portions in movies, my guess is, and this is very, very commonly done, is they've built the set in an airplane, and then they follow that path, and when they're on that downward path, then that's where they're weightless, and they can go ahead and float around like they would actually in space. Okay? So right here on the way up, they're experiencing two G's, 2 times the force of gravity, but on the way down, it's just 1 G. And then why do they curve back up here? Because they don't feel like hitting the ground. Okay? So that's probably a smart move. So there's the parabolic part right there. Okay? So, but another thing, wow, this I think is cool. Reflection. And let me explain. Okay? A parabola has a very special property that a lot of times people don't talk about. Okay? It has an imaginary point here that's called a focus. You won't need this for your test or anything, but this is just to try and stimulate your interest in what we got going on. If I've got some energy coming in, it's going to bounce off the side and it gets shot towards the focus. If I have some energy coming in here, the reflective qualities of a parabola bounce everything right to that focus. Can anybody think of a time where that might be useful? To collect information and focus it in on a point? Satellite dish. If you have a satellite dish in your house, you are using a parabola. Because what's happening? All this data is coming in, and that special shape of that dish focuses everything in on that point. Okay? And this is what's crazy. Raise your hand if you have a satellite dish at your house. Okay? So Molly's got one, Caitlin's got one. Anybody else? You've got one? Okay? So, do you think that the satellites are smart enough to say, I'm going to beam it at Molly's house, and I'm going to beam it at your house and your house? Do you think the satellite does that? So where does a satellite aim for? Everywhere. Everywhere. What's nuts is that you could put one of these anywhere here in Cumming County. Point it at the right spot, and you've got satellite. The whole countryside is being blanketed by that information, and all you've got to do is have that magic parabola. If we don't have this, and we just have that deal right there, it'll get a signal, but it's going to be way too weak. What this does is it amplifies that signal, gathers all that signal, and puts it at a point. Okay? So reflections happen in parabolic dishes. Parabolic dishes. And so we like satellite. And I always spell satellite wrong. Is it 2 L's?
Yeah.
2 T's or 1?
I think 1 T, 2 L's.
1 T. Okay, for like your satellite. Okay. Has anybody ever seen one of these on the sidelines of a football game?
Catch the sound.
It's to catch the sound. That's a parabolic dish. It doesn't look like it, but this is the very end of a parabola. Okay? So what happens there is all the sound is coming in, and even though if you would put the microphone there without the parabolic dish, you could probably hear it very, very faintly. But what happens is it collects all the sound energy that's coming into that dish, and it's reflecting it towards the microphone. Bounces, hits the microphone, bounces, hits the microphone, bounces, hits the microphone, bounces, hits the microphone. And that's what allows you to hear what's going out out in the field, like in a football game or a baseball game or whatever. Okay? So you guys haven't used this today, but maybe, this weekend you'll definitely see some or hear some evidence of that. But this is the thing that I think you may have used just as much as anything, is headlights. This is, instead of collecting information, it is reflecting light outwards. So you've got your filament, and then it hits the reflector, bounces out. 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 And then you've got this lens that'll either aim it down or aim it up or focus it or whatever. But it starts with a parabolic lamp. Okay? So anyway, those are just some examples of it. I just thought you might think that was kind of interesting to start with. Okay? So, today, here's what I want to do. I want you guys we have a good half an hour here. Here is your sheet with one problem. And yes, this is from the previous test format that I copied. You don't have to do these again. All you got to do is one problem and the bonus. So you're going to grab this, one problem and the bonus. You've got your other ones over here. I got a female stack. This is from yesterday. I got a male stack, and I've got a I don't know stack because there's no name. So once you're done with that...
Can I finish my thing?
Yeah. Oh, yeah. Okay. Once you're done with that, grab your other part, staple them together, and you're going to put it over here on the table. So once you're done with that, find your original, staple it together, put them on the table. And staple them in a way such that your name and the bonus will be on the back. So your assignment is just to finish that one worksheet. Yeah, so for those that are not here today, I'll see if I can find an example. Here we go. We're just finishing this worksheet. We are not going to do this worksheet today. Okay? We'll save that for later. We're just going to do this worksheet only. Okay? For ag people, my goal is I'd like you to try and have this test done by Wednesday so then I can hand it back. But that'll give you some time to get caught up. Hopefully things are going well.